linear algebra, basis in a topology. So this is a notion that we have in math where we want to kind of boil down complicated spaces to a few things, as few as possible. And they're uncountably possible here, but still it's easier to kind of think of the Euclidean topology as just being open intervals or unions of open intervals. So it's kind of easier to talk about even weird looking things using that concept. And that's why we use it. But you've seen it already, and you've seen it in linear algebra. We use in linear algebra E1, E2, E3. I'm just going to talk about R3. And you've done Rn. But if you take E1 to be, this is the math way of writing things, E2 to be 0, 1, 0, and E3 to be 0, 0, 1, that's called the basis. What's the notation you used in linear algebra? You took it. Did you take linear algebra? Did you guys use I, J, and K? I, J, and K? So but you did stuff with them. But these are the basis vectors for R3. And the reason they're the basis vectors for R3 is that any single vector can be written as a linear combination of these three guys. And they have other properties that are really nice. Do you remember them? They're orthogonal. They're also orthonormal. That if you take the magnitude is all one. So they're the prettiest looking basis you ever seen. And they look right. If you go draw your three-dimensional axes, they lie as the unit vectors on, depending on, we got physicists in here. So for us, X is this, Y is this, and Z is this. For you guys, Z comes out. Actually, this is the only time I'm going to say a physicist is probably doing it right, because you had the plane before when you were little, K through 12, there's a plane, and now you're at a third dimension, the Z should come out, right? But we're doing it the math way, X, Y, Z. What do you mean?
In this case, X, this is Y, and Z has to come out like with your finger this way. You know, something right now.
That might be why. I don't know why we did that E1, E2, E3 the way we did. It doesn't really matter to me because I know that everything can be expressed as these as a combination of these three vectors. So really, when I write a proof in linear algebra, I just write it for those three vectors. Once I do it for those three vectors, I can kind of work with linear combinations and show any other result I want. So it makes things easy. It doesn't seem like it when you're in classes. It's like one more thing to memorize, but that's why they're so nice. So if you have a vector B equals ABC, that V is really A times E1 plus B times E2 plus C times E3. Anybody have linear algebra from Dr. Clark? I'm sure he would have made you prove a few things using basis elements. So that's what makes it really nice. If I need to prove something about eigenvectors, I just expand my eigenvector into this basis combination, and then I can prove things about those basis vectors first, and then pull it up to the vector, the full vector. In the same way, how does basis in topology, how is that kind of resonating similarity to what you see here?
The same way you can union these unit basis vectors to form any vector in the space. You can union the basis elements to get any element.
That's right. Those are like the nuts and bolts of your topology. All the basis sets are like the basis vectors in R3. You can generate any element inside your topology using those basis sets. So it's the same concept. Does this make sense? All right. Another concept. In linear algebra is like the most important class. And if you're watching cartoons like I was in linear algebra, you're in a world of pain later because the professors always bring up linear algebra. It's a super important class. But in linear algebra, you have this notion known as span. Do you remember what that was? How many of you did not take linear algebra in here? Okay. You get a pass. You remember?
So the span is the set of all vectors that be created with the basis vector, with linear combinations of basis vectors.
Of those vectors instead of the set. So, right, so you start out with a set. Of vectors. I'm not going to put names to these guys. Let's just say I have two vectors. That set by itself is not what we call a subspace. It doesn't satisfy the criteria of being a vector space in itself. Because if I sum them, they might not still be in the space. That's one of the properties of a vector space, that if you sum two things, you can't jump out of that set. So it might be possible that I sum these two guys and I jump out of the set. It also isn't closed under scalar multiplication. So if I multiply V1 by some scalar, there's going to be a scalar that I can multiply it by where it's going to jump out of the set. So it's undesirable to have these two vectors by themselves. But then you can think of yourself as a witch brewing something and ask yourself, what do I have to add to this set to make it? What's the minimal number of things I need to add to the set to make it an actual subspace? And that's what span is. Consider. Sorry.
No good guesses.
Seeing the doctor with bad handwriting from isn't just that.
No, and my dad was actually a medical doctor, so it might be genetic. I think it was great when we taught 476 together. And Colonel Watts is not that much different either. So you got a definition in linear algebra where subspace was all linear combinations of the sky. It turns out that is true, but actually another definition of subspace is our span is it's the minimal one. It's kind of like the least common denominator. It's the smallest possible subspace that you can generate from these two vectors. I think that's a great theme to start out our class on, because your homework is exactly that question. If I have a collection of subset sets of an original set X, and I want to create a topology, what ingredients would I have to add to that collection of set? If I just take a collection of set, it's not automatically a topology. So what ingredients would I have to add to it to actually make it a topology? And I think that Michael's question to me at the end of class last time also fits into this. I was debating whether to show you this, but I think it's a little bit out of the scope of our class or where you guys are at, but it doesn't hurt sometimes to see things that you might not fully understand. So let's look at it. Okay, questions on this so far?
So,
That's actually the definition of span of S, not the one that's presented to you in linear algebra. I think you get this as span. It turns out that the span of S that the set that satisfies these two things also satisfies if and only if that space is going to be in linear combination with G1 and B2.
so for two, when it says T is another subspace containing B1 with B2, could you say that the span of S is a subset?
Oh, yeah, span of S, sorry. Thank you. Good eyes. Got it? Okay, so I gave you these weird definitions last time. Gave you this for homework. It's really hard to write live like this, Liz, but I'm doing it because you wanted me to. And I see it's actually much better in class for foundations when I do it this way. So these conditions are what I gave you on your homework. The conditions for a topology, let me put that in a different color. Let's see how well you remember them. Starts out almost the same. What's the definition of topology?
Set and the X are in the one.
Next one.
Union.
That's it. They almost look the same, right? The key piece is that this is not a countable union. It doesn't have to be. Intersection has to be finite. So this is topology. And this guy over here is something called a sigma algebra. And I gave you this problem and I asked you, gave you that side and I asked you, is this topology? I knew the answer. So this is one where Dr. T knew the answer.
Probably not, because why would they call this sigma algebra if it was really a topology? They just call it topology. So this is a completely different, gonna give you something different. And so I knew the answer already. And I had in mind that you're gonna pick an example. I thought I worded it actually great because a lot of you didn't realize, hey, this might not be true, and you went ahead and drove on and tried to prove it. And then so you have a proof now that is incorrect. And my idea was that's a great time to promote the idea of having examples first. That's step one to writing a proof is generate some examples. And I thought what would happen is you go, oh, finite complement topology is not going to work. Why doesn't it work?
It doesn't satisfy the second condition of sigma algebra.
Right. So that'll be a counterexample because if you take, by definition of the finite complement topology, A belongs to that topology if the complement is finite. But if the complement is finite, and you go back the other direction, it's not necessarily true that the other side is going to be infinite, finite, right? So just because B isn't the complement topology doesn't mean that C's complement isn't. And so it'll blow this. So Michael brought up, hey, that's an example of a topology that doesn't satisfy the definition of a sigma algebra. But what about the other direction? Is there, that doesn't prove the other direction, that if I have something that satisfies all these conditions, that it's not a topology. I knew it wasn't true, so I was in here telling, well, it's not true. But to come up with that example is actually pretty hard. But I'm going to show it to you anyways.
I wasn't going to initially, Michael. I sent you an email, but I thought, yeah, I'm going to show it to you guys. You won't when I show it to you.
Kind of field is sigma algebra.
Measure theory, probability, actually. If you go on to study probability, in my university, it was called real analysis. And they said, oh, you had an undergrad real class, so you can sit in this. I had no idea what they were talking about. It was actually taught by a probabilist. And probabilist, yeah.
Yeah, PhD in someone's program to require courses measured. Some programs don't.
That's even have been like the sigma that represents the standard deviation.
Yeah, different.
No, totally different.
So it's there's a random number that's you're talking about the right sigma.
There is no one.
When a sigma algebra can be thought of is allowable events that you can assign probabilities to. So for instance, the reason we had to do this is people are asking questions like, does it make sense to say the probability that you get an irrational number? If your data follow a normal distribution, right? Could you say that probability of getting an irrational? Could you say the probability of getting a rational? So you can come up with these weird counter examples where you're like, the Borel sets, like the Cantor sets, like,
Yeah.
does that even make sense to assign probabilities? So you need to limit the number of sets that you can actually look at and assign probabilities to, and that's what a sigma algebra does. It says, listen, your real numbers take on any, or your normal distribution takes on any real value. But just because that's true doesn't mean I can assign probabilities to any random set inside of the.
Ultimately, that's what you want to do. You want to assign probabilities to this guy. So we have something called a measure, which is the abstraction of probability that you learn in 476. And then you start taking measures of these sets that are satisfying these conditions.
Sorry, I get excited over this.
I knew when as soon as I saw you walk in here, I thought you're gonna love this. Okay, so back to the beginning of what I talked about.
You guys be nerd.
Yeah, it's like wine. It takes a while for it to age to a way that you'll like it. Because when you first see it, it's a shock to the system.
I'm going this way. Yeah. Geek out over technology for sigma algebra. Good, great.
Let me see if I can fix this up. Okay, so there we go. So now I'm going to show you an example of something that satisfies that sigma algebra definition, but is not a topology. And that was a little bit difficult to do because you have to go to this idea of measures, which I'm not going to do that. But I can do the same idea that I did with span. So I can start out with ingredients. And there is a part where you're just going to have to believe me because it just is out of the scope. Let's see what's happening here. Why did it shut off my? There it is. Okay, so let's say I start off with all open intervals.
And I want it to satisfy that definition of sigma algebra. Well, I have to start looking at those conditions and asking, what do I have to add to this set to force condition number 2, for example, to be there? I'm gonna have you think about this for a second. Maybe I'll have you take boards. I'll flash up the sigma algebra definition one more time. But if I have all open intervals that is in this set, what else might be in the set? So what I'd like to think about is, can you generate a closed set by using property 2 or property 3 or a combination of those? So if you can get closed intervals to all be in there, then that's a pretty big set, right? So formally closed, formally known as closed intervals. All right, so take boards and that. Just try to answer that one question. If I have open intervals as in this witch's brew, what else has to be in there in order to satisfy the definition of sigma algebra? Are closed intervals in there? Next question I have is, if you answer that one, are singletons in there? Like if there's a real number x by itself, singleton means just x in a set. Is that going to be, does that have to be in there? Right? Try it.